Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Hi, welcome to episode 24 of Driven. Today's episode is about safety watchdogs. Okay, safety watchdogs, what does that mean? And what does that have to do with autonomy, AI, and all the things that we're talking about here, robotics and much more? Well, safety watchdogs, and more maybe less specifically watchdogs, refer to those systems that kind of monitor other systems and check them for errors and other types of issues such that they can flag them and do something in response. And that's a watchdog in a nutshell. You might hear the term watchdog monitoring. Safety watchdog, as we're going to talk about here, is more specific to monitoring for hazards that may cause unsafe events with the system. And specifically, we're going to be talking about autonomous driving systems. So this episode is focused on the concept of safety watchdogs as it applies to, or can apply to, monitoring autonomous drive systems, or we might use the acronym ADS here, right? So these are autonomous vehicles that drive themselves and do all the things that we've talked about in episodes pretty much 1 through 23, right? So there's an AV course online on the Driven website where you can step through episode by episode and kind of understand what is an autonomous system, what is an autonomous vehicle. And so this episode obviously expands on that with specifically a discussion on how do we figure out whether or not these things are safe. So when we look at an autonomous drive system, these are arbitrarily complex systems composed of hardware and software components. Very often there's higher level programming involved with creating the software that runs inside these vehicles, or artificial intelligence, or artificial neural networks and deep learning algorithms that may be employed. In some cases, there's distributed processing, not only within a vehicle, but across the network. If you're getting data from the cloud in some autonomous vehicle applications, or in these connected vehicle applications, and vehicle to vehicle or vehicle to infrastructure type communications to make decisions. And there's just a whole host of other commercial off-the-shelf hardware and modern software frameworks that may be involved in creating these systems. So in each of these cases, very often, unless these components selected are specifically designed with safety critical systems in mind, they haven't been verified and validated to know that they're correct and complete, right? So there's a process for doing that. And this episode is going to talk about one method for achieving that verification and validation. So it boils down to the question, how do we make these autonomous vehicles, these robot cars, if you will, safe? How do we make them safe? And what is safety? What does that mean exactly? I guess if you take a really broad definition of the word safety, you might think about sharp edges and ways that you can cut yourself, and that has nothing to do with the system safety that we refer to here when we talk about safety watchdogs of autonomous drive systems. We're talking about the detection of hazardous events that can lead to an incident or an accident with the vehicle that could harm a person, that could harm some property, can harm an environment, harm something living or non-living, that would be unacceptable to society and humanity. So safety in this context deals with the detection or identification of these hazardous events and the prevention of that by providing assurance mechanisms to ensure that the system provides for the safety of the human being and the environment and the vehicle involved. So some sort of safety assurance methodology. Now, there are other types of assurance, and in some cases, people can confuse these different types of assurance. Sometimes people will confuse reliability with safety. Like, oh, we have to have triple modular redundancy to ensure that this system doesn't fail at all. And that's not necessarily safety. That may be more like reliability or availability, which are two other forms of assurance. Whereas safety just deals with ensuring that the system and the environment and the people involved are safe. And so that may be failing safe, right? Now, failing safe leads to a system that is not available. So it may be a less available system, so it affects the availability. It may not even be indicative of a reliable system because there's a component that fails that's not reliable. But if you're failing safe, you're guaranteeing safety. Now, one could argue, and people do argue, that the safest system is the system, or safest autonomous vehicle, I should say, is the one that doesn't move at all. Now, that's not a very useful system. It's not a reliable system, but it's a very safe system because it just doesn't move, and it may not even leave the garage. So that's a pretty safe system, but it's not very useful. So obviously, there are other aspects of assurance, systems assurance, that are required to ensure that the system and the autonomous vehicle is even usable. Is it reliable? Is it available? Is it maintainable? And is it secure? Security and safety can have a bit of an overlap. If you can hack a system, that may be considered a malicious event and lead to an unsafe situation, or it could just be a breach of privacy or a breach of other sort of security measure. But it could also lead to an unsafe situation, and therefore you still want to have a means for failing safe, right, in those situations. So safety, security, reliability, availability, maintainability, dependability, and safety and security are types of assurance that are involved with the design of any system. So one common methodology that people think of right out of the gate when you start talking about how do you provide for a safe system or a reliable system, another type of assured system, is to provide redundancy of hardware, redundancy of software, redundancy of components, such that if one fails, there's another available to take over and do something and continue on in the operation of that system. And there's different types of redundancy, right? You might have heard the word TMR, triple modular redundancy, right? Because you have three modules that are going to be running concurrently. Maybe they're all doing the same exact thing. And then there's some sort of voting mechanism that says, are all these systems agreeing at this moment in time to do the same thing? And if so, okay, let's proceed. If one of them disagrees with the other two, well, let's vote and say that what the other two are saying to do is correct. And of course, if they all three disagree, then you've got a problem. You've got a system failure. You could still fail safe, but you've got a failure of reliability or of availability of the system in that case. So if we look at a simpler situation where you have two systems, a primary autonomous drive system and sort of a secondary autonomous drive system that happens to be the exact same as the other one. It's the same hardware, it's the same software. You're just running the two systems, comparing outputs, getting inputs perhaps from the same exact inputs, comparing outputs. And if they agree, then you know that everything's okay. If they disagree, then you know there's a fault or a failure or an error in the system. Now, in this case, there can be common cause failures because you have the same exact system. If it's the same make and model of hardware, they may fail in the same way. If it's certainly the same software, they may fail in the same fashion. So that's what you might call homogeneous redundancy. But then there's also heterogeneous redundancy or diverse redundancy, where the two systems, in this case, the two autonomous drive systems, are actually different. So you have sort of maybe a primary system, and then you have maybe your secondary system, which is now implemented differently. Maybe it's running on different hardware. It could be also implemented using completely different software. They have a method called clean room development of software, where Two different software teams will develop an algorithm completely separate from one another, in sort of separate rooms, right? A clean room, and then you're running that diverse software on the two different systems and comparing the outputs. And if they agree, you move forward. If not, you flag an error and you move on. So going beyond diverse redundancy in that sort of pure sense, there's another form of diverse redundancy, albeit with a little bit of a different variation. And that's where the secondary system is not actually perfectly redundant with the primary system, but it's implemented to check or monitor the primary system. And in the event of a detected error or failure, it will fail safe. It will trigger the system to fail safe, right? And so this is leading us towards the watchdog monitor or the watchdog checking concept. And it's important to remember in all these cases, and we're going to talk about this in a little bit more detail, but if the software created for these diverse redundant systems are derived from the same requirement specification, if there's a failure in the requirements defined for these systems, there still may exist common cause failures. The diverse implementation, the clean room software team may have created the same exact error because it's derived from the same exact requirement specification as the team that created the primary software system. Likewise, the checking system, if it's derived from the same faulty specification, can be implementing the wrong check, right, against the primary system. And you still have an unsafe situation because the specification was wrong to begin with, and it fed both the development of the primary autonomous drive system and the system that's checking that system. So this again leads us to the concept of a watchdog. What is the watchdog concept? And the watchdog concept is simply this concept where you have this arbitrarily complex autonomous drive system being passively monitored by an independently developed watchdog processing-based system. This could be a computer with checking software on it that's independently monitoring the main autonomous drive system. Checked information is flowing from that system over to the watchdog, and it's verifying and validating that the system is operating according to what it thinks is the correct and complete way for operation. And it's typically a simpler process than, say, a fully redundant but different autonomous drive system, because the checking algorithms and the methodologies by which you implement these assertions or these checks, as we'll see, can be are just simpler by nature, or can be simpler by nature. In the most extreme situation, in the worst case, they're as complicated as the algorithms that you've implemented in the primary autonomous drive system. But more often than not, these are simpler methodologies, simpler ways to check and verify and validate that these more complex algorithms are operating correctly and completely. And if the watchdog finds an issue or an error, the system is designed such that it can fail safe. This may flag alerts, warnings to a driver who could potentially take over, or via remote or via onboard controls, or actually fail the vehicle in a safe fashion. In this case, it may be making the vehicle stop, if you can do such a thing. But if you're on like a major highway, the fail-safe methodology may be to put on the flashers and pull over to the side of the road, right? But it's a fail-safe mechanism, and the watchdog can trigger that. So watchdog specifications. Let's go back to this concept of feeding the system with the correct information to begin with, the design of the system to begin with. So most systems start with some sort of requirement specification. Now, it's true, some systems don't have specifications, or they don't have very good specifications at all, and that's a bad thing in general, right? The specifications may be written on the back of a napkin. They may not be very well verified and validated themselves. because these systems can become very complicated. Now, I'm joking. You should not be running requirement specifications on napkins, of course, but suffice to say that there's a document or a series of documents that define the functional requirements of the system, and perhaps even the safety and the security and the reliability, maintainability requirements for the system as well, other orthogonal requirements to the functional spec. But you have a requirement specification that's describing what the system should do. Now, not every requirement is safety critical. There are some requirements that may deal with displaying certain information that just happens to not be, critical to the safe operation of the system, or some other function, right, of the system that just has nothing to do with whether or not it can induce a hazard. But there will be a subset of an autonomous drive systems specification that is safety critical, such that if those requirements are incorrect, or if they're implemented incorrectly, and they are correct, the requirements themselves, then a hazardous event can occur and lead to a safety issue. So therefore, those are safety critical specifications. And that's typically a subset of the overall safety system. So in any sort of safety verification process, there's going to have to be some verification and validation that these requirements themselves are correct and complete. And now there's there are a few methodologies for that, I should say, but there's a lot of different variations of these broad methodologies that exist. So there's hazard analysis, where you're, in some cases, just going through the specifications and thinking through what are the risks, what's the likelihood of some failure mode happening, what's the severity of that failure mode, detailing methodologies for mitigating that. There may be failure modes, effects, and analysis methodologies, certain probabilistic methodologies for analyzing specifications, and more formal methodologies. There are formal methods where you can define the specification in such a fashion that it's easier to verify and validate that it's actually correct and potentially complete, right, for a subset of functionality that the system needs to implement. Now, for autonomous drive systems, this can be a very complicated process, because these systems are still relatively new in the world, right? Autonomous driving systems have not existed for the last 100 years, or even in some cases, I guess it's been about 15, say, years-ish commercially, right? It's still very much a research and development program in some other domains and applications. So autonomous drive systems, the specifications for these and the verification and validation thereof is a very important topic, and figuring out how to do that is a non-trivial task. But there are methods, there are traditional methods for hazard analyses that can be applied, and then out of that you can start to think about safety functions that can mitigate those failure modes that can arise from the safety critical subsets of functions that are being implemented. So you might have a function that says a requirement function that speaks to the fact that the vehicle has to be able to know its current speed, and you identify the fact that, well, if there's a failure in the computation of the speed of the vehicle, if we say it's traveling 5 miles an hour, but it's actually traveling 55, that could lead to a hazardous event, right? So the correct calculation of the speed of the vehicle, the correct sensing of that, becomes a safety critical function or requirement. And then there may be a safety function that says, well, I'm going to compare 2 different speed values to one another, or maybe 3 different speed values, and verify and validate that they're all reporting the same speed, plus or minus 0.1 mile per hour, say, for example. So now you can take these safety functions and go through a process of mapping these into safety checks that could then be implemented in the safety watchdog, right? It can be monitoring these 3 different speed inputs. It may actually drive the system designed to have multiple inputs for speed, independent inputs that can be read by the safety watchdog, whereas maybe the main drive system's only looking at one, but the safety watchdog is looking at all three, and it's comparing them to know whether or not we're getting the correct speed recording for the vehicle. And now then there's methods, of course, for verifying and validating that your mapping of these safety checking functions to the actual encoded rules, programmed rules that are getting loaded into the watchdog are correct and complete. And because these are simpler rules than, say, verifying and validating that this artificial neural network is perceiving that there's a human being out there, that's a much more complicated process. And in fact, it may not even be possible to verify and validate a neural network directly in such a fashion. But it's a lot easier to verify and validate these simpler watchdog checking rules, right? You can apply traditional methods for verifying and validating code and applying it to these rules, these watchdog checking rules. Now, as information is flowing through the system, the information itself could get corrupted. You may get a speed reading from a sensor that says, again, it's going 5 miles per hour, but it may have actually said 55 miles per hour from the sensor, and there was some bits that are flipped, there's some corruption of some sort, and now you're getting the wrong speed value from the sensor itself. So one methodology for preventing against that is also to maybe enforce the encoding of certain safety critical information in the system. And this may involve taking the information packet, in this case, the speed of the vehicle, for example, and again, in this simplified model, slapping on an identifier that says this is from speed sensor number 1, and that sort of uniquely identifies the information and the source location from where it's coming. Maybe slapping on a timestamp that says, okay, this is time t0 or time t1. Maybe that's a cyclic timestamp, or maybe it's just a raw timestamp, so that you know over subsequent reads from that sensor that the information's fresh and it's not stuck in some buffer or memory location somewhere and just being spit out in a repeated fashion. And then using redundant check codes, CRC codes, or other types of codes over all that information, such that you can encode the information. And if there's a corruption along the way, you can know that with the independent CRC code to check against the information to know that yes, this is the correct information packet payload, it's the correct timestamp and the correct identifier. Now, there's a lot of information that flows through an autonomous drive system, and you may not want to and certainly may not need to encode all of it, right? And so one facet of this will be to figuring out, similar to how you might figure out what subset of specifications you need to analyze for safety criticality, you might start to look at what's the subset of coded information that I need to look at for safety criticality, and maybe just encode those sensor inputs that are safety critical, encode those outputs to the vehicle control system that are safety critical. Certainly like speed, brake, throttle controls, steering controls, those are pretty safety critical controls, but a horn on the vehicle may be an alert that's important, but you may not consider it safety critical in this case. So you're going to be encoding information throughout the autonomous drive system. Perhaps you may encode the sensor information, you may encode the controls information, and you may encode the information that's being sent from the autonomous drive system to the watchdog, an independent watchdog itself, right? Whether or not you actually encode this information is a function of other factors in terms of like redundancy and maybe the ASIL specifications, which is like a certification level for knowing that certain types of hardware components are compliant to certain standards, because otherwise encoding all this information may be an expensive and daunting prospect, right? Unless you have existing components that have already been certified for certain safety levels, right? But nevertheless, if you don't have that at your disposal, you can bring encoded information to the system, where regular commercial off-the-shelf hardware, sensors, and controls can potentially be used with proper encoding of information, which is then checked by the watchdog along the way. So all this implies that there's a service, a watchdog service that's out there in the system, monitoring what's going on, looking at these encoded words, decoding them, making sure the information is correct and complete, and that the correct decisions are being made along the way. And so the autonomous drive system may be feeding this information to the watchdog. If the autonomous drive system doesn't feed this information to the watchdog, itself will have its own sort of expectation as to what information it should be receiving and at what rate. And if it doesn't get it, that information, that identified information at that timing rate, the watchdog can be designed and coded to, again, fail safe, because it's not getting the information that it's expecting from the autonomous drive system. So the watchdog system is not just getting these code words and decoding them and getting this information and determining if the information is correct. It's also making sure that it's coming at all, and that it's timely, and that it's fresh by looking at the timestamps. And so you're going to have these watchdog checking rules that are going to define sort of the input space and the input characteristics, the timing characteristics for the inputs that need to come into this watchdog, both from ultimately the inputs to the system, the autonomous drive system, and the intermediate results and decisions that are being made, and how they manifested information that's also being sent to the watchdog along the way. And if the watchdog starts to crunch through all this information and says, yep, this is right, this is right, this is right, it will say all is right with the world. There's no reason to fail safe. We can keep on going, right? And it might do this in a cyclic fashion. Might look at certain information every millisecond, every 10 milliseconds, every 100 milliseconds, every second, right? It just depends on what information it's looking at and the decisions it needs to make along the way. But at some point, if it's not getting information in a timely fashion, there's going to be a watchdog timeout, and it's going to therefore then sort of raise a flag saying, okay, we have an unsafe situation, we need to fail safe. Or if in the process of checking this information, it detects an error or a wrong decision being made by the autonomous drive system, it can then also flag this erroneous situation and cause the system to fail safe, right? And so there's a couple different ways that one might do this. And it's important to also design the watchdog service itself to be verifiable and validatable and simple. So these methodologies for not just running through the checks need to be verified and validated, but also you can't have like a single stuck fault if you're just raising a digital output flag that says everything's bad, or lowering it if everything's okay. If that gets stuck high or stuck low, depending on the failure mode, you can have a bad situation, because the watchdog might be saying, hey, everything's gone haywire here, but its ability to communicate and signal to the fail-safe system that things are bad may be in itself broken in some way, right? So typically a time varying type signature or output of information from the watchdog will be sent in such a way that another downstream sort of watchdog timer service, a simpler service, can be saying, okay, I'm getting this time varying signature from the watchdog, and it's telling me everything's okay in a time varying fashion, such that I know there's not like a stuck bit, and if everything's okay, things proceed. If not, we're gonna tell the watchdog reaction service to fail safe. And what does that mean? What is the fail-safe reaction service? And this can depend on the application. In an autonomous drive system, in a controlled environment, the simplest situation may be just to fail safe. So if this time varying signature drops such that everything's saying everything's failed, or if it misses a heartbeat or a bit, and the system needs to fail safe, it may simply apply the brakes, release the throttle, and depending on the application, either continue to control the steering or control, say, sort of the last commanded 10 steering values or something like that. There's different ways to fail the steering of the vehicle, depending on the application as well. But you're definitely going to be applying the brakes and releasing the throttle, and you may even have redundant. You're going to have redundant brakes. You're going to have redundant controls in these situations, such that you're not reliant on just one braking system kicking in this case, right? And so that's the simplest way of failing safe. Now, if this is an application on autonomous driving system that's on a highway, so on the East Coast, I-95, on the West Coast, the 101, you're not going to want to be traveling 65 miles an hour and just slam on the brakes in the middle of the highway. That in and of itself can be an unsafe situation. And so you're going to have a more complicated fail-safe situation where if it can't fail over to human-based control, either onboard or remotely, you might be putting on the flasher lights and slowly pulling over to the side of the road with redundant sensors, ultrasonics, or otherwise to make sure that you're not, going to be colliding with anything until you can get off to the side of the road and stop in a safe fashion. Now, that's a much more complicated fail-safe situation that, consumer automotive applications and trucking-based applications, when they take the driver fully out of the seat, need to think about, right? But in more controlled environment autonomy applications, it typically can be a simpler situation where you're just stopping the vehicle in its tracks, and if there is a human operator on board or in remote control, they can take over from there. So with all of this, it's important to note that when you're doing hazard analyses and a lot of this sort of safety analysis, it can all be very kind of qualitative, right? It can be sort of seem somewhat subjective in some cases, right? So there's an interesting fast byproduct of what can fall out of this as the methodology for implementing this is improved. If you employ formal methods and if you employ more formal methodologies for deriving these checking rules and you're relying on this encoded information, you can begin to apply certain probabilistic methods to quantify the safety of the system. In other words, quantifying what they call the mean time between hazardous events. You can derive the mean time between hazardous events mathematically. I'm not going to go into it here, but you can derive that from the likelihood of certain events happening and calculating the likelihood of those things happening and the likelihood of you being able to detect those errors and failing safe, right? Based on the design of the system. Of course, there's a lot of assumptions that are made along the way to come up with this quantifiable information, but suffice to say that this methodology lends itself to a path to quantify not just verifiable and validatable systems, but also quantifiable safety, which can be really interesting because when you start looking at neural networks and these other types of systems, you're going to have to rely on some sort of probabilistic methodology for assuming that the system is operating correctly to begin with. But with the safety watchdog, you might actually be able to have a more definitively quantifiable way to know that it's safe and secure, right? So the same methodology that we talked about here, this safety watchdog can also be a security watchdog because the methodologies for checking the information is very similar. In the case of a safety issue, there are hazardous events that are occurring in the world, right? These aren't human-induced per se hazards. These are failures of software. These are failures of hardware components, inadvertent, not purposeful, not malicious. that have just occurred, right? Errors in the system. And the safety watchdog is looking at these errors that result from these failures of the system and failing safe. Similarly, in sort of the cybersecurity or security facet of all this, there are malicious events. A hacker can hack in and change the speed of the speed sensor, make it tell you that the vehicle isn't moving at all, and when it actually is moving 55 miles an hour, or tell you that there's nothing out there in the view of the LiDAR or the radar in front of the vehicle, when in fact there is, right? And so these are malicious events, but it can result in the same sort of signature of sort of pattern of errors that can occur in the error domain and the information that's being presented or not presented to the system. So a lot of the same methodologies that we just talked about here for implementing these safety watchdogs can apply to a security watchdog. So it's more of an assurance watchdog or a safety and a security watchdog, right? Ultimately, at the end of the day. So this is a methodology that has had its roots in certain other industries. Certainly in the autonomous vehicle space, there's certainly different things that one has to consider in doing this, but it's nevertheless an interesting facet of what one needs to start thinking about bringing to the table for these autonomous drive systems that have these arbitrarily complex hardware, software systems, especially neural networks and artificial intelligence that are being employed in these autonomous drive systems. We need some methodologies, some ways, and some tools in our toolbox to verify and validate that the decisions that those systems are making are correct and complete. And the safety watchdog is one key tool in that tool chest. And I hope you enjoyed this episode. We're going to dive deeper on some of these subjects, especially as it relates to neural networks, in some upcoming episodes. So stay tuned, and thanks for tuning in today. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web, and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.